Hello everyone, and thank you for joining us. Good morning, good afternoon, or good evening, and welcome to today's webinar, Achieving Optimal Virtualized Server Performance for NFV in the Carrier Cloud, brought to you today by Ixia, Dell, and 6WIND. I'm Emily Ikuda, and I'm your moderator today. We have just a few announcements. Before we begin, we wanted to cover a few housekeeping items. This webcast is designed to be interactive. Between you and the presenters, the webcast console you are looking at can be completely customized. You can resize or move any of the windows that you have opened. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We will try to answer these during the live Q&A portion of the webinar. If we don't get to your specific questions during the webinar, we will follow up with you after the webinar. A copy of today's slide deck along with the on-demand webinar will be sent to you via email after the webinar in 2 days. You are also going to see a live Twitter feed in the console from Ixia where you can view and also tweet live. We are using the hashtag NFV. I'd like to introduce our speakers today. We have Wenjing Chu, Distinguished Technologist at Dell Research. Wenjing Chu is a Distinguished Technologist for High Velocity Cloud Network Functions Virtualization, also known as NFV, and Mobility Research in Dell. We have Jan Rappaport, Product Manager at 6WIND. As Product Manager for 6WIND, Jan works closely with sales, marketing, and R&D to define and implement the 6WIND Gate roadmap in coordination with 6WIND's ecosystem of partners and customers. And we also have Michael Howe, Product Marketing Director at Ixia. Before beginning Senior Manager Market Development for Layer 2-3, Mike worked as a Senior Product Manager at Ixia for the last 5 years, overseeing IX Network, IX Automate, and IX Reporter. He also led Ixia's Carrier Ethernet business segment, growing it significantly over 5 years. Now I'd like to begin the presentation portion of the event. I'm going to turn the controls over to Michael Howe.
All right, thank you, Emily. Well, we have a lot of content to deliver here, and it's going to have to move at a pretty quick pace to get through it. So in the next 15 minutes or so, I will take you through the drivers for network function virtualization. Also, for the folks kind of ramping up on this technology, I've included a few slides to provide an introduction into the components that enable NFV. And then as we get into the heart of this particular presentation, we'll take a review at the bottlenecks and performance issues in terms of enabling NFV in a virtualized server platforms. And I'll provide a brief overview of the Ixia solutions to go lab to live. And so to get on with the content here, what's happening in our industry? Well, first of all, it's an exciting time to be working in tech, and it's largely driven by the innovation that's occurred in cloud computing. So what's cloud? I mean, cloud is really a multi-tenancy data center, and via cloud, applications are arriving that are changing the way we live and work and play, right? So you have things like Netflix video on demand. You can access it on any device as long as you have decent internet connectivity. You have tools that our businesses are using like Concur and Salesforce and Office 365 that can easily scale. And these kind of things are really useful to enterprise IT and enabling companies to scale up much faster as they hire more employees or are changing the way they progress. And how are these services all being delivered? Primarily through the cloud service providers. I listed a few here, but like Amazon and Rackspace, the Microsoft Azure cloud, and also via private cloud. So there's private clouds being leveraged to deliver these technologies as well. So with the progress in innovation at the cloud, how's that impacting the carriers? So what you see is the carriers are looking at this saying, wow, the cloud technology has moved so fast, and what we're doing with our networking technology has not moved that fast. And as a result, we are being limited to just the bandwidth provider, and these over-the-top providers are gaining the revenue. So carriers around the world are kicking off initiatives at reassessing the future of their networking technologies. And as they look at the network, they're looking at virtualization in two primary areas. The first is leveraging virtualization to reduce CapEx and OpEx. So that's taking what they do today and how do you save money in terms of the operational expenditures and the CapEx expenditures by leveraging virtualization. So this would enable service agility. It would align capacity to cost as opposed to the old model of purchasing equipment that needs to last in your network for 5 years doing capacity planning. It also will simplify the management of multi-vendor networks. And so the motivation is clear to try to leverage virtualization technology in terms of just taking cost out of the business. But beyond taking cost out, they're saying, how do we drive new revenue? How do we add value to the network, and so we're not just enabling bandwidth for over-the-top players that are taking a premium of the revenue? So looking at new network as a service model, looking at these technologies to enable dynamic moves, adds, and changes. These can be things like bandwidth calendaring or bandwidth on demand enabled through self-service portals that the customers can use. It can also enable new network services we haven't even realized that are possible yet. So this can be, location-based services, realizing where you're at, connecting to the network, and being able to push ads to you or things that are regionally important. It also means optimizing the network or using the network per application. So if my application needs low latency services or high bandwidth services or particular QoS settings, establishing the network services to dynamically support those application needs. And so what we're talking about is moving from cloud as we know it today, which are based on primarily centralized data centers, into telco cloud, which are built to deliver network services. So moving on from that, advanced the slides too quickly there. How has this all come about, this movement towards network function virtualization? Well, in 2012, a number of carriers got together and organized through a European organization called the ETSI, and they formed an industry study group for network function virtualization. So at the time, it was about 12 or 13 carriers that wrote a white paper and basically articulated the vision of what they want to do. Since that time, there's over 220 participating companies that participate in the ETSI ISG. And so what we're talking about here is taking functions that we do in the network today, which are firewalls, routers, deep packet inspection, WAN accelerators, even testers, and moving them from running on appliances that are, established or provided by independent vendors, have their own operating system, their own way to manage it, moving those to run in software on standard server platforms, so running them on x86-based standard server technology. So essentially leveraging the technology used in cloud today to run network functions essentially in the cloud or in the data center. So this is a fundamental shift. And where the ETSI is at is they've completed 2 years, and in 2 years they've accomplished what is known as Phase 1. And in Phase 1 there were 5 deliverables that included 4 specifications covering use cases, requirements, and architecture and framework and terminology. And they've also enabled proof of concepts. And so through that, they're coordinating and promoting members to work together to showcase real examples of this technology. So I highly encourage you to check out the ETSI page to learn more about that. So moving on, in the architecture and framework document, they provided some high-level, let's say, architecture of what the vision is. And so let's start with the bottom box, which is the NFV infrastructure. So how do we build this? So first, it's based on physical compute, physical storage, and physical networking, so your hardware resources. You then insert a virtualization layer, which is commonly referred to as a hypervisor. On top of the virtualization layer, you then have virtual compute, virtual storage, and virtual networking. So this is essentially, where the components are deployed. So once you have that virtualized infrastructure in place, you can deploy virtual machines. And in this case, instead of the virtual machine being something like a web server or a database or an application, you're going to be deploying virtual network functions. So you're taking traditional functions, routing, firewall, BRAS, and deploying them as virtual machines running on this infrastructure. And the box on the right is very important as well, because you can't deploy these things without the ability to manage and orchestrate them. So It's a very key component. These things must tie into the OSS and BSS systems. So let's take a quick look at the players. Just a little snapshot is, of course, Dell is the leader in providing the compute. In the virtualization layer, you have companies like VMware. You have the Linux distribution that provides KVM. Citrix is XenServer. Microsoft has a Hyper-V hypervisor, and quite a few others. In fact, you're hearing about more and more of these popping up. When it comes to the virtual network, this is extremely important as well as how do we tie these things into the network infrastructure. You have a lot of innovation here as well, and this is where OpenFlow becomes relevant in the discussion, where OpenFlow and OpenFlow-based technology or any SDN-based technology can provide the network connectivity network layer. So Alcatel-Lucent's Nuage, you have startups like PlumGrid and Big Switch, and many others in this space. But usually those technologies touch or basically replace or provide the vSwitch, which is the virtual switch used for the network connectivity. In the virtual network functions, nearly every player you know and love today providing routing, firewalling, load balancers, EPCs, I mean, you name it from a network function, they have virtualized their product lines. So this has really happened over the last 2 years, and this is just a small snippet of the names that exist. In the management and orchestration, this is where OpenStack-based technologies are becoming very important, where OpenStack can orchestrate the provisioning of the compute and the network resources. And there's a number of companies that are providing orchestration to help deploy the networking and compute required to build services. So next slide here is a good example of an end-to-end network service. This is referred in NFV terms as a service chain or a forwarding graph, where you have multiple functions that are stitched together to provide an end-to-end service. This is a good example of the complexity that you can have in that if you have a virtual CPE connected to a virtual firewall, to a virtual load balancer, you need to interconnect these technologies, and that can happen via a software-defined network overlay. You could provision the networking directly with OpenStack plugins. So there's a number of aspects here that are options to make this all work. And I think as you look into the ETSI POCs, the proof of concepts, you can see various ways that these are being accomplished. So this next slide, I know it's a little bit busy here, but I wanted to try to give you the big picture of how this all would interwork. First and foremost, to the lower right, you have the data center, and really this becomes the heart of where the services live. They're installed, the functions are installed as virtual machines on virtualized servers. So to instantiate virtual machines, you need orchestration, sometimes referred to as the VIM, the Virtualization Infrastructure Manager. So the orchestration must talk to the data center to handle the deployment of the virtual machines, which are the network functions. Orchestration also needs to talk to the network. So this can be through a software-defined networking controller, something like an OpenFlow controller. You've probably heard about Open Daylight. There's other choices out there like Juniper's Contrail and Floodlight from Big Switch and many others that can provision network connectivity and resources. And more, as you see these other bubbles of networking technologies, as you have the WAN and the optical network and the access network, more and more SDN technologies are going into those other areas as well, because you will need end-to-end connectivity. And in fact, if you look at what the ONF's doing with OpenFlow version 1.5, there's extensions to provision optical networking. So SDN is expanding. But you can see this is where it gets quite complex. But when I look at this diagram, there's one common theme jumps out, which is APIs, right? Programmatic interfaces to the data center, programmatic interfaces to the network, and to be able to build and deploy services on demand. So with all these pieces together, how do we roll out carrier-grade services? How do we roll out predictable performance that you can deliver reliable services to wrap service level agreements around? So we built up this kind of layered approach, which is when you buy an appliance from a vendor, the operating system, the network interface card, the internals of it have already been verified. When you change that model and purchase a virtual function and go to deploy it on standards-based hardware and software, there are a lot of variables that come into play. So first and foremost is the server platform, which you'll hear a lot about from Dell in the next segment. But what CPU technology are you using? Are you using the Intel Sandy Bridge or the newer Ivy Bridge? Are you using AMD's? What NICs are you using? So what physical NICs? They're provided by companies like Mellanox and Intel and others. Are you running 10 gig NICs and 40 gig NICs? Do your NICs have drivers that support Intel's DPDK? All of these things will impact the performance of the overall system. On top of the physical server, you're then installing a virtualization layer called the hypervisor. So the KVM will act and have slightly different performance characteristics to VMware. And as you look at different flavors of KVM, depending on who you're getting it from, if it's from Ubuntu or Red Hat or others, there's different feature sets that are part of that. I want to point out that last year we helped facilitate a test that the ENTC ran as part of an NFV showcase and white paper. And what they found in that paper was the vSwitch, the actual virtual switch or the networking as a component of the hypervisor, was actually the bottleneck of many tests. And so several companies that were providing virtual functions were saying, oh, you have to bypass the vSwitch to achieve optimal performance. Well, that kind of breaks the architecture. If you're bypassing the vSwitch, that vSwitch is required for your networking connectivity. So I think, even a year ago, we were seeing a lot of challenges. There's been a lot of innovation. Companies like NTT have come out and said, we found issues with KVM, but we've actually contributed a lot back into the code base to bring KVM up to a carrier grade to improve performance. I think you're seeing better performance, and we'll get into some of that as we move on. Moving up the stack, how the guest OS, each virtual machine will run a guest OS, and it will communicate back through the host OS, which is typically Linux. And so how those interact can create bottlenecks, and even the virtual functions themselves, how they've been written to use a multi-core CPU, how they've been written to use memory, are they multi-threaded? There's a lot of aspects here that will impact the overall performance. So there's more variables in the test. So speaking about test, as we look at rolling out NFV, here's kind of the life cycle of it, which is what are the goals? What are we trying to accomplish? Are we trying to virtualize individual functions like EPC or a firewall? Or are we trying to do service chaining? So you kind of really define what you're trying to do. And the next phase you're looking at, will it work? So this is the functional testing, proof of concepts, and this is what's been taking place over the last few years. Then you move on to will it scale? And looking at scale and capacity as you look at building carrier-grade services. Then you roll it out into pilot networks, and once it's out in the network, it's really all about managing and monitoring and understanding if you're delivering to the service level agreements. So how Ixia, we're a bit unique in this case, is that we have our traditional solutions which are focused on testing. So the Ixia chassis you know and love through acquisition of Breaking Point. We have the industry's leading security performance testing. We have the new Perfect Storm solution. We have a product called RackSim, which allows you to test scaled virtual infrastructure. So our product line, from a test perspective, have been in the development in the QA phase for many years. We also, through acquisition of Anui and Breaking Point, have moved into the monitoring space. So here we're doing, tap ports, Anui and NetOptics. We have tapping and tool optimization to optimize your monitoring tools. As you look at our virtual solutions, we began virtualizing our Ixia solutions nearly 6 years ago in an attempt to enable development testers to test. And so we have a virtual platform called IXVM, and on that virtual platform, our IX network for layer 2, layer 3, and our IX load for layer 4, layer 7, we already have virtual edition applications there. So It's very useful as you look at doing the virtualized testing. And then for end-to-end verification, we have our IX Chariot. So IX Chariot, starting with 8.0, is completely built for virtual environments. You can install the console as a hypervisor. You can install endpoints on essentially any operating system or VM and run application performance testing. And then another cool piece of technology we have through the NetOptics acquisition is the Phantom Virtual Tap. Phantom Virtual Tap allows you to tap into the hypervisor and look at communications from an individual VM to the vSwitch. So essentially providing visibility into the virtualized infrastructure. So just a very quick look at how IXVM deploys. I'll build this out quickly, which is you have a host virtualized server. The green boxes are VMs that are deployed, which are Ixia, essentially virtual line cards. On those line cards, you have VNIC interfaces. We require one VNIC for management. Then the second, or up to however many VNICs the hypervisor supports or vSwitch supports, can be used as test networks. So then we have a VM also for our controller, and then you network it out to your lab management, and you run applications like IXVM or IX Network, and you can control the virtual port. So in this case, you can test the performance of a vSwitch. You can network them into testing individual network functions that have been virtualized or service chains. I want to take a quick look at, in the scale and capacity testing, we worked with a firewall vendor and looked at performance testing of a firewall. We tested their appliance, and then we tested the firewall as a virtual machine. Just to quickly show you the results, and you can download the full paper at ixiacom.com/NFV, the rightmost box, the 95 was scored as the firewall standalone appliance. When we ran the firewall as a VNF, a virtual function, allocating 2 gig, which is the default, it scored a 65 in the breaking point resiliency test. By going up to 4 gig of RAM, we're able to increase the performance of that virtual firewall to 78. Now, it's still not equivalent to the appliance, yet this gives you decisions. Do you run more virtual instances? Do you go from a centralized model to a more distributed model? But it's really important to look at comparing as you move from an appliance to running virtually. In some cases, you may have better performance. In many cases, you may not have the same performance, and needing to understand that. So real quickly, for more information in detail about what I discussed, you can check out our, again, linked from ixiacom.com/NFV, and you can download our ebook on NFV. So I know I moved fast. Hopefully it was good information for you. And I will turn it over to Wenjing from Dell to learn about the latest platforms from Dell. Wenjing?
Thank you, Mike. That was a lot of information, very fast, and but make my life a lot easier. So now you get all the background of NFV and what it is all about and why the industry is after. I would like to probably take from that and look at really fundamentally what's the problem we need to solve. So Dell, as before I jump into that topic, has been the forefront of NFV since the very beginning. So we've been participating in ETSI. We have several proof of concepts to really working with our partners and to really understand and drive the initiative in the industry to have a ecosystem that's healthy and really be able to deliver the promise of network function virtualization. So in that endeavor, we're really happy to have Ixia and Ixia as our partners. And for today's webinar, I think the core question that, when we start out doing this, is looking at the real importance of performance. And Mike alluded to you're looking at performance very evaluations of a virtualized network function versus a physical appliances. And to really achieve the benefit that NFV promises, we need to not only be able to have the predictable performance or the carrier grade we typically use, but we also want to achieve that with unconstrained virtualization. Essentially, to have the portability and the elasticity, because that's where the other goal is to get a very high operational efficiency, so that the economics of the data center can be really applied to a carrier network infrastructure. And so, from looking at the design, the architecture of NFV, the core really to achieve both goals at the same time is a very highly optimal virtualization performance. And you need to build a system to be able to achieve both of these critical technical parameters that will really allow you to not only be able to really stand up the network functions in a virtual cloud, but also have the operations and management system be able to very fastly move your resources around and achieve the operational efficiency. So let's look into a little bit more detail. And this is, again, based on a lot of a study once you get into the picture on the right, how the data actually going to pass in a virtualized system. Right? So, you guys or many of you may have experience on virtualized network functions. For example, a virtual firewall in a cloud or in Amazon. Most of the impression we have will be that it's very convenient, very interesting to use, but can they really replace the hardware infrastructure in your data center? Or in a big question, like can they really replace the carrier-grade large-scale systems in the operator's network? And those are the questions that we have to be able to answer with certainty and with the service level guarantees that we need to have before the NFV becomes reality. And here the folks in ETSI really look into and summarize the 4 challenges, right? So the challenges we the first challenge that Michael alluded to was the many factors that depend on the processing the performance. It could be related to the hardware, could be related to network adapters, processor architecture, and the operating system you use, the hypervisor details, and a slew of other things, memory architecture, for example, and how much memory you have, and what percentage of your code or your data lives in the cache. So all that comes into play. And I think it's a very big challenge that Dell embarked to do is really to solve those problems with software so that we have a platform that hidden all the details from developers of higher level network functions. So that becomes a platform that's universally applicable to anyone who wants to really have a virtualized network function that can work the same way but have great performance and be able to migrate within the data center from point A to B with very little cost. So that I think that's the key for us to achieve those goals. The second challenge I want to point into is the interconnection of virtual network functions. So VNFs are different from a typical high-performance server application. So, take the example of a lot of high computation, for example, in scientific computation or in databases or e-commerce. The requirement here for network function, again, think of them as a firewall, a router, a load balancer, or anything in between. Right? It could be a 4G wireless network for evolved packet core, for example, which is really doing a lot of packet forwarding from in different directions. So the interconnection point is where your bottleneck is going to be. You're going to have a lot of packet going in and out from these points. And as the topology of your network becomes more complex, which they all are in real life scenarios, the performance point of those exchange point, it's really critical. So we would like to know not only how efficient that can be done, but also what is the upper limit that we can achieve with off-the-shelf commercial standard servers. So there's always a discussion about the difference between a normal virtual machine that we all know and very popularly used today, and a network device. I think it's really important that we look into the nature of a distributed system for networking. The other aspects of it, for example, include the much smaller packet size that you will see in the network. So other than in a server, a lot of database or large amount of data movement in the computing domain, usually the packets are pretty large, and it's relatively easy to handle. In the network domain, when you look at the media, right, videos and voice tend to have much smaller packet sizes. So that increase the message, the number of messages you have to process in every second. So there's a common problem of scalability in in really how many packets or messages you can handle within the system. Related to that is the number of sessions. So we are talking about how many concurrent sessions are ongoing, and I think there's a lot of well-known challenges when we come from a few thousand to a few hundreds of thousands to a few millions. Now I think we're looking at hundreds of millions of these active sessions in the network. So think of all the mobile phones you have. Each one could have 10, 20 live sessions at any time. And so you factor in a few millions of customers in the metropolitan area, and you get the picture of the scale we could have to handle. All these also goes into future requirements like the Internet of Things, which will probably increase this number even further. So combined together, really, just highlights the need for high performance, and this not only goes into the high performance of a particular function, but really looking at all these different factors we have to achieve. Challenge number 3 is really the dilemma really between virtualization and predictable performance. And the virtualization naturally, or in a traditional way at least, that creates additional overhead and creates the uncertainty or the distance between an application and the actual computing resources. So there's an uncertainty introduced in between. So that reduces the predictability as well as the overall performance. And the number 4 challenge, I think it has to be simple to manage. This is really coming down to I would say, the most important benefit of cloud computing and definitely network function virtualization is that we want to be able to achieve the operational efficiency. So that's the core driver to achieve this, to make it a lot easier to deploy a service, to modify, to adapt to live conditions, and provide a much better user experience to the end users. So in summary, these are the issues we face as we go into working with our customers, our operators, who we've been doing a lot of proof of concept and trials over the years, and I think there are many other challenges, but the core to really allow NFV industry to stand on its feet is really have this virtualization layer in place and performance at the same time. So as we, trying to answer these questions, I thought a very useful thing to do and to the industry at large, and to really showcase the tremendous advancement in software, in hardware, and definitely the improvements that the industry has been making to optimize all the virtualization layers. We talked about newer architectures, and I think that the system we're going to be doing is R920 from Dell. It's a huge workhorse. It can do so much. I think we want to share with you as an example, right, that this is really true for all the new generation of servers. And Dell is actually announcing a new generation in the last few days. So the performance of these machines will improve even further. And we all know that the exponential rule of how these things are being evolving, which is another reason that virtualization is critical for the industry, because it allows us to achieve the benefit of software and the benefit of cloud computing while riding this ever-increasing curve of computing capacity. Right? So the question we want to really showcase is what it can really do. And in this example, we have a R920 with 4 sockets of E7 8800 series of processors, and in a lot of cases, people start to think about how do you saturate 10 gigabit Ethernet interfaces, and so we want to move to the next level to saturate 40 gig, and as we are at it, we want to say, how about make all 6 of them, so that's 240 gig of traffic. And can we do it? Can we do it, with real-time properties? Can we do it with enough processing power left to do the actual applications? And so we like to try this out, and you can find better partners than Ixia and 6Win, and to really put this system together and see what we can do for virtualized networking and switching in single server. Right? So I specified some of the details on all these software we use and the hardware we use in the benchmark. And the key thing here is that we use open source, OpenStack, KVM, Linux, and Open vSwitch. And I'm going to leave the details of 6Win software that Yang's going to capture a little later. And so this is it. This is what we want to set out to do, to answer that question. And can we have performance, not just kind of close to hardware appliance performance, but actually a lot better, I think. This is a single server. So imagine that you expand it to the whole rack, expand this to the whole rows of servers in the data center, and you get a picture of NFV, and that's really what we need to get to, go beyond a physical box and let it, live in a data center that you can shape and fact any way you want, right? I didn't put in the picture too much detail, so I want to just simplify so that you can really get to the point across very easily. But behind all these things, there's a network fabric that is software defined, and it's a 40 gig today, and we can go into 100 gigs very soon. So that network fabric, and Dell is a leader in that space as well, allow these servers to seamlessly connect together and give you any kind of application a really a space to grow and scale in a shape and form you like. So for folks who are really, really technically oriented, want to get into the details, I'm providing this particular picture that is it's a 4-socket architecture, and how the PCIe devices are connected, and which each of them allow us to support 40 gig today, and we're working at with Mellanox. We'll be also working with Intel and others. We'll probably be looking at 100 gig pretty soon as well, and this allows if you have a large scale network that need a high level of really interconnectivity, right? This is what you want to, the hardest knuckle you have to go crack. So this demonstration really answers the question of the promise of virtualization software. It's a promise of what it can achieve. I think we should look beyond the sort of emulation of our hardware appliances to the next stage, which is really thinking your solution in a cloud computing environment, and say, what is the best we can do? It should be a lot better than a single unit hardware appliances. It would not only achieve very, very high performance within the confine of a one single physical server, but that performance can be scaled both upwards and horizontally to much larger degrees. So with that, I just want to have some sort of concluding remarks on the design choices and use cases. While the benchmark we've done is focused on 20, and like I said, all that designs, and as you look into the architectural connections of how that works, apply to really any of the modern infrastructure and data center systems. On the use case side, I think we've been using this platform to showcase in mobile and internet access networks, in the edge network of service providers, as well as to virtualize the CPE space, and a lot of content distribution for media. So these are just a few examples of that, and the whole industry here, I think, it's the size of $200 billion every year. So we're looking at doubling the entire cloud computing space in the next few years. And it's very exciting, and again, we are happy to work with Ixia and Fixwing to really realize these visions. And with that, I'm going to pass to Yan from Fixwing.
Thank you, Wenjing. And hi, everyone. So, yes, as we are running a bit short on time, I'll try to be quick on some of my slides. I want to explain to you today the network performance challenges introduced by NFV. I think Wenjing and Mike have done that quite well. And especially I would like to explain how our 6-winged high-performance packet processing software addresses these challenges. I will illustrate how 6-winged can be used in an NFV environment as the networking foundation within the NFV infrastructure, as well as in the virtual function, in the virtual network function itself. So first, the industry move the transformation towards NFV from proprietary hardware platforms to virtual applications running in a virtual environment totally independent of the hardware is enabled by, of course, new hardware architectures, but also, and this is very important, by the ecosystem of the standard Linux operating system and innovative packet processing software that will allow for performance comparable to ASICs or FPGA-based solutions with the flexibility of software. What we see today in an NFV environment is virtual machines running on top of a hypervisor, providing the NFV infrastructure, or NFVI, and telecom operators are pressing technology providers to provide them with means to virtualize the network nodes that accomplish certain network functions, such as PGW, IMS, HHS, BNG, etc. The NFVI has to provide high throughput between VMs and the outside world, while preserving hardware independence, and also high-performance VM-to-VM communication for service chaining use cases. So standard implementations based on a virtual switch do provide hardware independence, but they don't provide the right level of throughput for communication between VMs and between a VM and the outside world. This is due to bottlenecks in the operating system of the hypervisor, in the virtual switch implementation itself, and in the communication channel between the hypervisor and the virtual machines. An alternative to that is to use SRIOV. SRIOV removes the performance bottlenecks of the hypervisor. With SRIOV, a physical NIC exposes a number of virtual functions that can be attached to VMs. VMs see each attached virtual function as if it was a physical card, same brand, same model as the real physical card. And in this case, throughput is improved, but hardware independence is lost. The VMs run NIC-dependent drivers, the number of VMs in the system is limited by the number of virtual functions, and latency is high. To preserve the benefits of virtualization and provide the right level of performance, a new packet processing software architecture is needed. This is where 6-winged comes in the game. As the standard Linux operating system has a lot to deal with apart from pure packet processing, we have designed the 6-winged packet processing software to run on dedicated cores, isolated from the Linux operating system. This software consists in a high-performance networking stack called the FastPath, designed to provide the highest throughput and the lowest latency. Packet processing is offloaded from the Linux operating system. The packet processing performance scales linearly with the number of cores running the FastPath, so that 6-winged users make the most out of today's modern multi-core processor platforms. We get the fastest performance on the market in both physical and virtual environments. The FastPath is transparently synchronized with Linux, so that existing Linux applications don't need to be modified. 6-winged users continue to use standard Linux configuration tool, and they benefit from the FastPath packet processing performance. The FastPath is available for all major multi-core hardware vendors on the market, including Intel, Cavium, Broadcom, and EasyChip Tylera. And finally, the FastPath supports an extensive set of layer 2 to layer 4 networking protocols, including IP forwarding, IPsec, TCP UDP termination, Open vSwitch acceleration, and more. So the FastPath is transparent to the operating system. All packets received by the FastPath are processed very efficiently if the recall information is here to treat the packets, and if not, the FastPath is going to rely on Linux through the exception mechanism, and the continuous synchronization mechanism will make sure that any information learned in Linux while packets are processed is synchronized to the FastPath, so that the next packet of the same flow can be entirely processed by the fast path. So 6WinGate is transparent to existing Linux applications, Linux management, hypervisor. In terms of performance, so 6WinGate removes the performance bottlenecks of Linux. The CPU resources necessary for packet processing are drastically reduced so that less cores are necessary to process network traffic at higher rates, and Linux stability is increased. Performance scales linearly with the number of cores dedicated to running the fast path. We achieve 200 gigabits of Open vSwitch and more, as we will see in the next slide, 190 gigabits of IPsec, and 220 million packets per second of IP forwarding performance. So what's our solution for NFV? 6WinGate can run the hypervisor to increase virtual switching performance. First, it supports standard VNIC drivers for existing VNFs and can also be combined with 6WinGate accelerated VNFs to reach bare metal performance while preserving the benefits of virtualization. So let's see that in detail. .6WinGate NFVI in the hypervisor offloads virtual switching from the operating system. It relies on DPDK to receive packets very efficiently into the fast path, which provides OVS or Linux bridge acceleration combined with extended network services such as IPsec, NAT, etc. VNF drivers support standard virtual appliances based on VirtIO, whether they are DPDK-based, Linux-based, or based on other OSs. And for the best performance, 6Win's fast VNIC drivers can be used. Fast VNIC is available for DPDK-based or Linux-based virtual appliances and is essential for other OSs. Compared to a hardware-based solution, 6WinGate, which is software-based, allows very high performance VM-to-VM communication, and so bypasses the 50 gigabits bandwidth limitation of the PCI Express and enables a 500 gigabits bandwidth with low latency for VM-to-VM communication. So that's about 6WinGate in the hypervisor. And now, if you remember well, this can be combined with 6WinGate in the virtual machine, where 6WinGate brings high performance layer 2 to layer 4 packet processing software, so that you get over 10 times Linux performance. It extends the DPDK with support for multi-vendor NICs and crypto acceleration. It is transparent to Linux and to its management, and it can be used as such to build virtual network functions such as vRouter, vBRAS, vEPC, vCPE, or vIPsec gateways. 6WinGate is a modular offering, so our customers choose their abstraction layer on top of the hardware they want to support. We call this the FPN SDK. On Intel, as I said, we provide DPDK extensions for multi-vendor NICs, crypto, and virtualization. This allows to bring hardware platform independence to the 6WinGate fastpath, which provides a very large set of data plane protocols from layer 2 VLAN link aggregation, GRE, MPLS bridging, through layer 3, forwarding, multicast, tunneling, NAT, filtering, IPsec, QoS, TCP, OVS acceleration, of course, and more telco protocols like L2TP, GTPU. This data plane foundation is generic software that can be combined with third-party control plane protocols because we are transparent, but also with 6WinGate control plane protocols if you wish. And we complement that with our distributed architecture extensions that allow you to run the control plane and fastpath on different CPUs, and high availability extensions so that our customers have a complete protocol portfolio for VNFs. In the case of 6WinGate NFVI acceleration, we have done a performance comparison of IP forwarding throughput in a VM. We've compared standard Linux with 6WinGate accelerated NFVI and standard Linux in the VM, and 6WinGate accelerated NFVI NVM. And so in short, because we don't have much time, we see that standard Linux brings around 500K packets per second per core and does not scale very well with the number of cores used in the host and the guest. With 6.8 NFV, we reach around 2 million packets per second of standard Linux VM forwarding performance that scales pretty well up to 6 million packets per second. And when 6.8 is used in both the NFV and the virtual machine, we go from 3 million packets per second on one core up to 23 million packets per second, which is 30 times Linux performance. And our latest demo illustrates this with an accelerated Open vSwitch example. 6.8 runs inside the hypervisor to accelerate the standard Open vSwitch on openvswitch.org. We do this by offloading packet processing from the Linux Open vSwitch data plane to the 6.8 fastpath running on dedicated cores. 6.8 leverages 6.8 DPDK and the 6.8 Mellanox PMD to receive and send packets efficiently into the fastpath. The fastpath has its own flow table to get the highest level of performance. This does not require any modification to the standard Linux OVS control plane. In addition, OVS acceleration can be combined with other fastpath protocols such as VXLAN, NAT filtering, IPsec, and more to provide enhanced services at the hypervisor level. And with a 40-core Dell R920 server populated with 8 40-gig Mellanox NICs, we have demonstrated using an Ixia traffic generator with 40 gig NICs, 255 gigabits of virtual switching performance using 8 fastpath cores, which means that 80% of the cores remain available to deploy VNFs. So in summary, 6.8 enables the network architecture transformation by delivering the performance required to replace legacy hardware with commodity servers and virtualization. We do this transparently with no change to the existing infrastructure. With our 6.8 packet processing software, customers enjoy over 10 times performance improvements with no change to Linux, the operating system, hypervisor, virtual switch, or management. For our customers, we know that speed matters.
Thanks, Jan, for that. And now we'll enter into our Q&A portion of the webinar. Please click on the Q&A widget at the bottom of the console to submit your questions. If we don't get to your specific questions during the webinar, we will follow up with you after the webinar via email. I'll now queue up the first question. This one is for Wenjing. Slide number 15. What software function was loaded on the Dell R920?
So let me go back to the 15. So the software we've essentially here's how you build a software. You have OpenStack. And I think we use Red Hat as OpenStack, but any OpenStack should work. We use KVM, and Jan mentioned there's a modification to KVM to improve for carrier performance. We put on Linux as a host and Open vSwitch. So again, you see these are standard Open vSwitch. Without changes specifically for network function virtualization. And then we have a six-wing gate, and Jan just described in detail. I think those are the main components of the software.
Yes, and what's important, if I may add, is that really standard software is used, and 6.8 just runs transparently for this software, so that the high-level management tools can be used without any modification.
Yeah, specifically, for example, if you have an SDN controller, all those work normally.
Okay, and I have a follow-up question to that. So Dell servers with WinGate optimization, both from a WinGate VM and WinGate driver standpoint, are used to run on Ixia's network packet broker software function. Is that correct?
Is that a question about Ixia's Sorry, I wasn't quite sure the last point.
So I think I can take that. So actually the 6-wing-8 is running on the Dell server as a device under test, and we put that in front of an Ixia packet generator who has its own Ixia software running on it that can generate line rate traffic. So 6-wing-8 is running on the Dell server and is being benchmarked by the Ixia.
Yeah, if you look at that picture again, the Ixia can be configured to do different tests. So it could be we're doing virtual switching, that would be just packet switching test. You can vary different sizes. If it's an SSL, IPsec, then you run different software. But Ixia is really a great system to allow us to really generate that much traffic. We need in the full setup, I think we need 8 to up to 10 different 40 gig interfaces to drive the system under test. So that's and we run several different tests, so that all combined using the different configurations of Ixia. Back to you, Emily.
Emily, are there more questions? You might be on mute.
So we have 2 more questions. What is the maximum vSwitch throughput you can get with 6-win 40 gigabits, 80 gigabits? How many cores are required to achieve this max throughput?
Yes, so that's a good question. The thing is, the answer depends on your use case. So in the demo we've done on the Dell R920 servers, we've demonstrated 255 gigabits of throughput. So that's using 6-wing-8 software, and we've used 8 cores of this server. So it depends. If you have to run many VNFs in the system with the Dell R920, which has 40 cores, you'll be happy to have still 32 cores available for your VNF and 255 gigabits with only 8 cores for the fast path. Now, if you want much more throughput, you can use more cores of the Dell server. If, for example, if you don't have any VNFs, if you just want to do a software switched based on this server, then as 6-wing-8 performance scales with the number of cores, you can just multiply this throughput by the number of cores. Of course, you'll have to populate the server with the right number of NICs, but that is feasible. And I think what's important is really to identify the use case, identify the throughput for the vSwitch, of course, but the throughput for the VMs, and based on that, design the system, design the number of cores you need for your VMs and the number of cores you need for the vSwitch. And if you take a standard Linux solution today, if you want to reach numbers in the tens of gigabits, you'll use almost, if not all the cores of the server just for the virtual switching, and you will have no cores available for your VMs. So with 6-win, as I said, we reach this demo 255 gigabits with just 20% of the cores for the virtual switching.
Yeah, and I think that 20% is really a kind of something number to remember. We're seeing that for all the different scenarios. If you're looking at packet switching, the rule of thumb is that it can do it within under 20% of the load in the system. The only other parameters you want to consider is, of course, all the PCIe devices and how it's connected with the cores. So sometimes that limits how much you can pump into, no matter how much the processing can be done. So in our practice, I think you have full really freedom to stack out your system, and usually processing is not the bottleneck.
Thank you. And with that, we are over time now. If we did not get to your specific questions, we will follow up with you after the webinar. I just wanted to thank everyone for attending, and we hope you enjoyed the webinar and hope that you learned something. We do have a special thanks to our participants from Dell and 6Win. Some really good material, and for the audience will be made on-demand version of the webinar, and some helpful materials will be sent to you in a follow-up email. We hope that you join us for future Ixia events in the future. Thank you, everyone.
Thank you, everyone. Bye.